So, now we are going to get somewhere. So, we have derived this beautiful equation J n is minus beta I S n C n by F n t. Now, they are very interesting thing to look into that. Now, if I have against n, I am using the corner because I need to talk of this equation quite a bit now. Now, this is my free landscape, okay, and this is my critical thing. Now, here at small n near n equal to 1, at the limit and in the scale when n is very large, n could be of the something like 200 or 300 typically, then in this region particles are trying to go and come back and there is enough of them. So, this is the region, it is like equilibrium. So, when I go to the limit n going to 0, I am entitled to going to 0 because I have made n into a continuum. Actually, it does not go below n equal to 1, but mathematically that does not make any difference whether I took 1 or 0 does not make any difference, as you will see. Okay. So, n going to 0 or n going to 1, f n becomes C n. However, when n goes to infinity, that means n goes to infinity means here all the way there is nothing there. Okay. Before that I have the minimum maximum, after maximum it just goes downhill. So, n going to infinity, this quantity f n t is 0. Okay. This is third is the most important thing. In a steady state when there is a flow of train, that is what I did flow of train. I again appeal to you to remember that a train is going towards in front of you and one after another the compartments are coming one after another in regular interval. Train has a constant velocity speed, constant speed. What does it mean? That means our case, what is happening? Our compartment are n minus 1, the next compartment is n, the next compartment is n plus 1, they are steady state flow. What does it mean? That means J is independent of n. Now, I have this wonderful expression now, J is independent of n. So, what do I do now? And I know the limits. So, I immediately now write down now I can do an integration because I know the limits. So, I do the integration 0 to infinity. Okay. So, I bring d here, I bring dn here and then I do this integration 0 to infinity and infinity it is 0 and at n equal to 0 infinity f n t at that limit. So, there is a d here, so it just goes, this become evaluate at n equal to 0 and n equal to infinity. Now, n equal to infinity is 0 and n equal to 0 f n equal to C n. Okay. So, I just and there is a minus in front, that because it is lower limit I just get 1. Okay. So, then I get the beautiful relation J equal to I am almost there now. So, this is minus 1 in front bracket minus 1. So, that means my beta I and beta I and Sn, because they are in denominator of denominator, they comes out. So, now I have the following expression. Right. So, I have to evaluate this thing now. Now, let us do a little bit. So, we have done the main thing, we have a little faster rate I will go now. So, this is the thing I said, since the equilibrium prevails for smallest clusters, this Fn by Cn goes to 1, but when n goes to infinity, this goes to 0 because of actual post critical size is rare, actually not rare, it is not there. Then so now I have to calculate the rate. Now what do I do? So this is my Cn, this is beta Isn. Okay. Now I need, remember I need the at the critical cluster. So Sn become Sn star or Sn C, and then I have to evaluate this integral now, and so important thing to assume that this is minus, note that this particular integral that I have to do this integral that I have to do, it is 0 to infinity, but I will come to minus infinity to plus infinity. Then I write Cn, the minus 1 is there, Cn is Cn equilibrium C then e to the power, I say okay, I want population here. So because I have an integration to do, so I now say this I write Cn, but because this is a method called method of steepest descent, or many other goes by Laplace's formula, many methods. So basic idea is that around here Cn is very small in this region, Cn is very small in this region. If Cn is very small, then that is it is in denominator. So in the integral over dn, this quantity here it dominates, and so then I say okay, C is I can now consider only a small region around here. So the way I would do that, then I will say okay, Cn is the Cn star, and then this is a harmonic, I assume it to be harmonic, and I write the fluctuation here n minus n star square, and then I need to do the double derivative, because this I expand the delta g here, delta g n as delta g n star plus delta g double derivative n minus n star square by a factor of 2. Okay. So that is then by 2, and by kBt is here. Then it becomes this now so let us explain this again. It is a little tricky. I have to do the integral, so I have to do this integral. this integral I am going to do, and this integral I use the following property, that this Cn is very very small here, and this Cn is very small, and this is the smallest Cn in this landscape, which is Cn is e to the power minus beta delta Gn by Boltzmann distribution, and this is maximum, this delta Gn is maximum. If delta Gn is maximum means Cn is minimum. So, in this integration Cn is minimum here. So, 1 minus Cn is maximum here. Okay. This is, I am saying this is used again and again. So, Cn is very rare in a barrier top. So, 1 over Cn it peaks, and so it is enough in this integration to take care of the region near the maximum. That because of this advantage that we are taking, that the advantage that Cn is this quantity is minimum. So, 1 over Cn is maximum. We expand it in a harmonic thing, and this is second derivative, and then this is Gaussian. So, I can now do this integration completely. So, everything before I have done that, I have the beta Sn. So, beta Sn and 1 minus 1 of Cn star, that will come up. So, that is, so this is beta Sn, my earlier thing, Cn star coming, because I am making approximation, Cn is Cn star, then the Gaussian. So, that inverse that comes from. So, this is fully documented by me. I know Z is the leftover of the integration, and that integration I can do because this is Gaussian function now. Okay. So, minus infinity to plus infinity, I can make it also 0 to infinity, I do not care, because there is this integration is so sharply picked, the function, it is n star, it is so sharply picked that I can always make it to minus infinity without any loss, minus infinity as it is given here. Then this integration is just 2 pi to root over 2 pi by a, and the Gaussian integral, and that gives now the delta G square, 2 is there, and the 2 pi kBt. So, I now get this beautiful expression, the rate of nucleation so everything is determined. I have now I have rate of nucleation, this is given by Zeldovich factor Z, rate of impingement beta I, that comes from kinetic theory, surface area and the critical concentration, that has to be there, we know that, and it is just reproduced beautifully, and Cn star is given by Boltzmann concentration of monomer, because I start here and go there, this is the monomer and this is the n star. So, that is given by n star, my probability of being here is given by this expression, and my impingement surface is giving that, and this Zeldovich factor is called the non-equilibrium effects that take into account of going the both ways. This is exactly we do in chemical kinetics, we sometimes call that Smolkowski equation approach. And all these things happen very similar time, and it is exactly what is Kramer's theory also of chemical kinetics, very well known theory of chemical kinetics that we will do little bit hopefully someday. So, now what is zeta? What is Z? Z is this beautiful expression, let me write down that. That delta G second derivative by 2 pi kBt. and rate is Z Lovich factor, impingement, surface ratio, Cn star. This is the rate of nucleation. The reason I did it in detail, in such great detail, and more detail is given in the book, and of course I think what I did here little bit more straightforward than what is given in the book. Book is little bit, I think some more detailed steps and little bit more talking has been done, which is not necessary. So basically the summarize the whole thing is that we did a calculation of the rate of barrier crossing, is a very standard thing in chemical kinetics and many other things, but Zeldovich did it without knowing anything, but around the same time Smoluchowski did this barrierless connection, Lindemann did, Michaelis-Menten did, and all these things all at the same time, the same thing, and this is a very general approach. The formula of this 2 pi kBt root over this thing is essentially goes as Laplace's formula. And so, a few more comments we have done. So, this is what I was talking about, the temperature dependence, a very strongly temperature dependent phenomena. The supersaturate, sometimes it is not just a temperature but pressure, and supersaturation, that means you increase the pressure, you see nucleation, that is the way to see the nucleation in a cloud chamber. And these are the different supersaturation. The supersaturation S3 is more than S2 than S1, and then when the supersaturation increases, the size of the nucleus comes down, and barrier comes down. So, activation free energy decreases. The reason is that if you transfer into free energy landscape, then what is happening is that as you increase the supersaturation, then this delta GV, which is delta GV, this quantity is increasing. As this quantity is increasing, then R star is decreasing, and delta G star 16 pi by 3 gamma cube by delta GV square. This is also changing, but this is changing much faster. So, as we increase supersaturation or in a lower temperature, we call it increased supercooling. Like when water instead of 0 degree centigrade, I am going to minus 10 degree, minus 20, this you can say minus 5, minus 10, minus 20, below the freezing, and then the barrier comes down, as I said, and the size comes down. Then what is really interesting, you find that nothing is doing, you go on, suddenly it comes explosive, like it is shown here. The rate of nucleation suddenly increases, because the barrier has to come down to a level where thermal fluctuations can access it, and that exactly happens. So, this is the picture, very important picture of the nucleation theory. Next is that as both free energy difference between bulk phase and surface known for several systems, notably for water and many other systems, a quantity verification nucleation theory is possible, and it is there are certain limitations. They are very detailed things, like the surface tension we are using is that for coexistence, but we are using it in out of equilibrium. So, there is certain limitation there. Then we assume it as a sphere, that is a limitation there, and many times they are little elliptical, simulations have showed. And then core of the nucleus is really liquid like, but surface, nucleation, we are assuming this is sharp boundary, and core is that of the new phase and this is the old phase. That is not quite like that, because this is some extent it is core like, but then there is a diffuse region, and that is also an important thing that we have not discussed, and that is done by theory called density functional theory of expression, that we can do only when you do the density functional theory, which I will explain little bit density functional theory later when you do the density functional theory. And there is this beautiful problem heterogeneous nucleation, and that heterogeneous nucleation is described like that. You are on a surface. Then the basic idea is that surface tension of you reduce the exposure of the liquid to the old new phase to the old phase, and the surface tension of this could be much less, and as a result you get a free energy barrier that is the heterogeneous nucleus, which is the barrier gets substantially reduced, and the amount it gets reduced is a quantity psi theta w, which is given by this quantity. I am not going to derive it, it is another long derivation, but theta w is determined by this, theta w is determined the surface tension of this surface tension and this surface tension, and that is the expression that is given. So that this heterogeneous nucleation barrier comes down, this is homogeneous nucleation, but to describe heterogeneous nucleation you need homogeneous nucleation, theory of homogeneous nucleation, and so that expression is not given here, but it is kind of said that if the angle is 90 then barrier becomes half, if it is 3/8 then barrier becomes much less, 0.375. So this is an important thing, and there are many other things which we would be describing later. So we will start next a little bit of Ostwald's step rule, then we go over to some other aspects of statistical mechanics, and that will be in the next class.